Alright, so in this video I'm going to be explaining another important article about domain adaptation. And the title of this article is Overcoming Concept Shift in Domain-Aware Settings Through Consolidated Internal Distributions. As I said, we have different types of domain shift. We have concept shift, we have covariate shift, and we have label shift. We also have conditional and other different types of domain shifts. But in this paper, we only focus on this concept shift. So this paper in 2022, and it leverages the definition of concept shift from this article in 26. So we develop an algorithm to improve the performance of pre-trained model under concept shift without retraining the model from scratch when only unannotated samples of initial concepts are accessible. We model this problem as a domain adaptation problem, where the source domain data is inaccessible during model adaptation. The core idea is based on consolidating the intermediate internal distribution learned to represent the source domain data after adapting the model. We provide theoretical analysis and conduct extensive experiments to demonstrate that the proposed method is effective. When monitoring sensory data from a wearable device, the context oftentimes changes abruptly. People move from one situation, for example, working quietly in their office, to another, being interrupted by one's manager. These context changes can be treated like concept shifts, since the underlying data generator, the concept, changes while moving from one context situation to another. So when you go from this USPS to Street View data set, you will see that we have a concept shift. So here it's just 3, but here, although there are some features that looks like 3, but it is 35, so it's a different label. So there is a concept shift. So consider a source domain which consists of the distribution and labeling function f. So given a family of parametric functions, for example, a deep neural network, our goal is to solve optimal model with minimum expected risk. So it's a proper loss function. Architecture of the proposed method, you will see that on the top, we have a neural network is trained on a source domain with annotated data. The internally learned distribution at the output space of the encoder is modeled via a Gaussian mixture model. The bottom, the model is updated to address concept shift in a target domain with annotated data by matching the target domain distribution with the GMM using pseudo dataset. So in order to circumvent the challenge of distributional gap between the two domains, we can decompose the mapping into a deep encoder and a classifier subnetwork. So Z denotes the intermediate embedding space, that latent space that we have seen in many videos in this playlist. So given theta hat, if we adapt phi such that the discrepancy between the source and target distributions is minimized in the embedding space, then the classifier will generalize well on the target domain, despite being trained using only the source labeled data points. Many prior classic UDA algorithms use this strategy but implement it by assuming that D sub S is always accessible. This makes computing the distance between the distribution feasible, and hence it reduces to selecting a proper probability metric and then solving. The major challenge in sequential model adaptation is that, as opposed, the term cannot be computed. We need a new approach to estimate. So we propose to solve the challenge through aligning the source and target indirectly via an intermediate internally learned distribution in the embedding space. So we set a softmax function at the output of the encoder just before passing data representation into the classifier. So the classifier can be assumed as a maximum posterior, so map estimator, which assigns membership probability distribution to a given point. This assumption implies that when an optimal model is trained for the source domain, the encoder would transform the source distribution in the input space into multimodal distribution with k components in the embedding space, each corresponding to one class. Thus, internal distribution emerges because the classes should become separable in the embedding space as a result of learning for a generalizable model with a softmax layer. This internal distribution is a multimodal distribution in which each distribution mode would capture one of the classes. Performance degradation occurs when shifts in the input distribution violate boundaries between the classes in the embedding space. If we update the model such that the internal distribution remains stable in the target domain after model adaptation, for example, the source and target would share similar internal distribution in the embedding space, then the classifier would generalize fill. So we consider P is just a Gaussian mixture model. So it's a linear combination of this normal distribution. So prior probability for each class, we have this mean and covariance for each component. So we consider that Gaussian mixture model. So since we have labeled data points, we can compute Gaussian mixture model parameters using map estimates. So let's S sub j denote the support set for class J. Sometimes people use Gaussian mixture model in the context of multi-source or domain generalization, that they have multiple sources. But in this paper, it's just single source, but we have k classes. So that's another way that you can use Gaussian mixture model. So don't forget that we only have one single source, one single source domain and one single target domain. But we compose our source, so this is our source, we compose it into some classes. Because we have labeled data for source, so that's another naive approach for decomposition of your source domain, so that each one is a different class. So let's carry on. Let S sub j denote the support set for class J in the training data set. So we can estimate just the mean and covariance very easily. Our major idea is to use this internal distribution estimate to circumvent the major challenge of sequential model adaptation. So we draw random samples from the internal distribution estimate and generate a labeled pseudo data set. So we solve this alignment problem. And this D measures this probability distribution. It's a discrepancy measure. And lambda is just the trade-off parameter between the two terms. So D, as I said, D denotes a probability distribution metric to measure the distributional discrepancy. So our generated labeled data set is like this. And the labels are ascribed according to classifier subnetwork prediction. To generate a clean pseudo data set, we also set a threshold tau, this tau, and include only those generated samples for which the classifier prediction confidence is greater than tau. The sequential model, then we solve this alignment, as I said before. So let's carry on. We have given your source data set, these are the input of the algorithm. Then we train the source domain. We know this. Then we have internal distribution estimation because we are decomposing into some classes, as I said. For example, mu j and cj is the mean and covariance of the class J, so we can easily understand them. Then we do model adaptation. So given your target data set, first we create pseudo data set generation. Then we draw data batches and update the model by solving this equation. So when you go from different source to different target, you can see different classification accuracy. For example, for these data sets, MNIST, USPS, SV, HN, Street View. And the state of the art is now this. Or maybe these are very easy data sets.